So we have the problem number 1. The order and degree of the equation 1 plus d2y upon dx2 power 5 by 2 is equal to dy upon dx. So we have find the order and degree of the equation. So this equation dy upon dx square can be written in the form of, if we take the whole square both the sides, then we will be getting 1 plus d2y upon dx2 to the power 5. Okay. Let me first write like this: d2y upon dx2 to the power 5 by 2 is equal to dy upon dx square minus 1. Or further, we can have d2y upon dx2 to the power 5 is equal to dy upon dx square minus 1 whole square. So from here, if we expand this, then we are getting the greatest order derivative as 2. So order is 2 and the power of greatest order derivative is 5. So degree is 5. Okay. So order 2, degree 5. Order and degree. That means option 2 is correct. Okay. Now we have problem number 2. The order of a differential equation of the family of circles with one diameter along the line y is equal to x. So the family of circle has a diameter along line y is equal to x. So we can say that center lies on this line. So we have the coordinate for center as, say, alpha alpha. So we can write the equation of a circle as x minus alpha square plus y minus alpha square is equal to some radius square. Okay. So if we see in this equation, we have two independent parameters, that is alpha and r. So two independent parameters are there in this equation. So we have the order of differential equation to remove this parameter is 2, right? So we have to differentiate this equation 2 times so that all the parameters will get reduced. Okay. Okay, that all the parameters should vanish. Okay, we have to differentiate it minimum number of times so that all parameter gets vanished. So that minimum time is 2. So order of differential equation we are getting is 2 from this case, right? Okay, now problem number 3. The order of differential equation of all tangent lines to the parabola y is equal to x square. So we have a parabola y is equal to x square. Okay, so we can write this parabola in form y is equal to that is x square is equal to 4 times 1 upon 4y. So we have its parametric form. As 2 into 1 by 4 t, 280 and 80 square, 1 by 4 t square. So we have parametric form as t by 2 t square by 4, right? So that x square is 4 times x square is equal to y, right? So we have parametric form as t by 2 t square by 4. And if we try to find the slope of the tangent, so dy upon dx we are getting 2x, that is 2 times 3 upon 2. So t is the slope of tangent in terms of parameters. So if we try to write the equation of tangent, then y minus y1, which is t square upon 4, is equal to m slope, which is t, x minus x1, that is x minus t upon 2. So here also the tangent, in the equation of tangent, we are getting only one independent parameter, that is t. So differentiating this equation, once we will be getting rid of this value t, right? So the order of differential equation must be 1. Okay, so A is the correct answer. Now problem number 4, the equation of the curve which is such that portion of the axis of x cut off between the origin and the tangent at any point is proportional to the ordinate of that point is. So we have a curve whose equation we have to find such that portion of the axis, see, let us draw the axis. Say this is x axis, this is y axis, such that portion of the axis x cut off between the origin and the tangent at point, say this is origin, and let this curve is y is equal to fx, and we are taking this tangent at this point, we are considering tangent at this point, so we have a tangent something like this. Okay, let us take this point as A, so this must be AFA. Okay, so the portion of the axis of x cut off between the origin and the tangent at any point is proportional to the ordinate at that point. Ordinate of this point is FA. So we have the relation, this length is something which is k times the ordinate, right? So we have the equation of tangent at point AFA as y minus FA is equal to m, which is f dash A x minus A. So finding the point of intersection of tangent and x axis, we have to substitute y is equal to 0. So x is equal to A minus FA upon f dash A. Now distance between this point and origin is this point itself, right? So this is proportional to, this value is proportional to the ordinate, right? So we have this value A minus FA upon f dash A is equal to k times FA. Let us write A in general as x and FA in general as y, so that f dash A is dy upon dx, right? So we will be writing, in place of A we will be writing x minus, in place of FA we will be writing y, dx upon dy is equal to ky. Okay, so from here we are getting an equation which is in the form y dx upon dy is equal to x minus ky, or we can write dx upon dy is equal to x by y minus k. So this is homogeneous differential equation. So if we substitute something which is t is equal to say x upon y, so dt upon dy, we can write it in the form of, if we substitute t is equal to x of y, then we can write x is equal to yt, or dx upon dt, we can write it form of dx upon dy, and then dx upon dy can be written as y into dt upon dy plus t. Okay, so y into dt upon dy plus t is equal to t minus k. Okay, so we have dt cancelled, so we have dt is equal to minus k dy upon y, or we have now integrating both the sides, we will be getting t is equal to minus k ln y plus some other constant c. So now doing reverse substitution, the value of t is x upon y. So we have x upon y is equal to minus k ln y plus c as the solution of our differential equation. So let us see the options. So if we arrange the terms, we will be getting, let us arrange the terms of our solution. So we have x is equal to minus ky ln y plus cy, which is equal to minus y into k ln y plus c, minus k ln y plus c. Okay, so from here we see that option A is correct. Okay, now moving to the next question. The curve which satisfies the differential equation, the given differential equation is x dy minus y dx upon x dy plus y dx is equal to y square sin xy and passes through 0 1 is given by. So we have the equation which is x dy minus y dx upon x dy plus y dx is equal to y square sin xy, and the curve passes through point 0 1. So x dy minus y dx upon y square can be rewritten as minus of y dx minus x dy upon y square, which is nothing but minus of dx upon y, right? Similarly, x dy plus y dx is same as dxy. Now substituting these two on the above equation, we have minus of dx by y upon dxy is equal to sin xy. So we have minus of dx by y is equal to sin xy dxy. So integrating the equations, we will be getting minus of x by y is equal to minus of cos xy plus some constant c. So putting the value 0 1, x is equal to 0, y is equal to 1. We have 0 is equal to minus 1 plus c, right? Because cos 0 is 1. So we have c is equal to 1. That means the equation is minus x upon y is equal to minus cos x by y cos xy, right? Cos xy plus 1. So which means that x is equal to y times cos xy minus 1. Okay, so from here we say that option A is correct, right? Okay, now moving to the next question. We have problem number 6. If y is equal to fx, be a differential function, then for all x which belongs to real, which of the following is always true? Okay. So there is a relation between the derivatives. So we can write dy upon dx as dx upon dy inverse, right? Now differentiating both the sides, because see, why we are doing like that? Because we have a relation in dy by dx and dx by dy. So we write dy by dx as in form of dx by dy, and then we are differentiating to get second order differential equation. So we are differentiating with respect to x both the sides. So d2y upon dx2 is equal to, differentiating this, x to the power minus 1, the differentiation is minus 1 x to the power minus 2. So we have the differentiation of dx upon dy with respect to x as minus 1 dx upon dy to the power minus 2. Now differentiating dy upon dx. Okay. Dx upon dy with respect to dx to get d2x upon dy2. Okay. So from here we have we can write this as minus dx upon dy to the power minus 2 d2x upon dy2. Okay. This can be rewritten as d2y upon dx2 times dy upon dx square, okay, plus d2x upon dy2 is equal to 0. So from here we see, let us check the relation. Dy upon dx is dx upon dy to the power minus 1, differentiating with respect to x both the sides. In LHS we are getting d2y by dx square, whereas in RHS we are getting dx upon dy to the power minus 2, and again the differentiation of dx upon dy with respect to x. Okay. So this is equal to dy upon this is dx upon dy to the power minus 2, right? Okay. Now here we have to differentiate. Once we have what we have done, we have differentiated this with respect to x, but we are differentiating this term with respect to y. So again one term will come which is dy upon dx. So here in place of dy upon dx square it should be cube. Okay. So if we check the option from here, option B is correct, right? Okay, fine. Now problem 7. The solution of the equation y plus x root xy into x plus y dx is minus y plus y times root xy into x plus y dy is. So let us first write it in the form of dy by dx. So we have the expression for dy by dx as y plus x root xy times x plus y upon y plus y root xy times x plus y. Okay. Now let us divide this whole term by y. That means let us divide the denominator as well as numerator by y. So we have the expression as 1 plus x upon y. Okay. or say let us put, see, this is basically homogeneous form equation. So we can substitute y something which is similar to x, like say we are substituting y is equal to kx. So from here we are getting constant k, from here we are getting root k, and from here we are getting constant k. So the equation is not actually homogeneous. Okay, so if k terms will be getting cancelled, then we can say that the equation is homogeneous, but there is we are not getting the case like that. So we have to see some different point. So we have the equation. Let us write the equation in the form whatever it is written in the problem. So we have the equation as y plus x root xy x plus y dx minus y plus y root xy x plus y dy is equal to 0. Right? This is the given differential equation. So we can write this equation in the form x dx plus y dy plus y dx minus x dy upon root under xy into x plus y. Right? If you separate the terms, then we can rewrite the equation in this form, right? So now differentiating with respect to x, we are getting here x square by 2 plus y square by 2 plus or let us write is equal to x dy minus y dx is equal upon x square under root y upon x 1 plus y upon x. Now this differential equation is homogeneous. Okay, so we will be integrating this equation this side. So this is homogeneous, so this can be integrated now. So we have x square plus y square upon 2 is equal to 2 upon 1 plus y by x d of root y by x. Right? If we substitute t is equal to root y by x, then you will be getting this form. So from here we have the equation x square plus y by x square plus y square is equal to 4 tan inverse of root y by x plus e, because this is the equation of form dx upon x square plus a square, right? So from here we can say that option B is correct. Okay. Now moving to next question. The equation of the curve passing through 2, 5 and having the area of triangle formed by x-axis, the ordinate of a point on the curve and the tangent at that point as 5 square unit. Okay. So let us have a curve y is equal to fx. This is say y is equal to fx. Okay. At point A we have a tangent. Say this is a tangent at point A, and here it cuts the x-axis. So we have this is A and here it cuts the x-axis. So we have the area of this triangle given as 5A. So let us draw the triangle again. This is the point AFA. Okay, this is the point A and this is the point where tangent cuts the x-axis. So again we are writing the equation of tangent as y minus f a is equal to f dash a x minus a. So putting y is equal to 0, we are getting x is equal to a minus f a upon f dash a. Okay, so the base of triangle can be written as a minus f a upon f dash a minus a, right? So we have area of triangle A as f minus of f a into f dash a into its ordinate f a. This is equal to 5. So let us write y is equal to f a if x is equal to a, and dy by dx is equal to f dash a. So we have, in place of f a we write y, so we have minus of y square is equal to 5 dy upon dx, or we can write dy upon y square is equal to dx. Okay, so integrating we are getting 5 into 1 upon y square is y to the power minus 2 plus 1, which is y to the power minus 1. So 5 into 1 upon y is equal to x plus c. So we are getting 5 upon y is equal to x plus c as the solution of differential equation. But in question it is saying that the curve passes through the point 2, 5. Okay, the curve passes through the point 2, 5. So this equation must satisfy that criteria. So we have x is equal to 2 and y is equal to 5, satisfying this curve. So we have 5 upon y is 5 and x is equal to 2 plus c. Okay, let us see. See, the area of triangle is half into base into height. So we have half times this into this. So this is actually 10, right? This should be 10. So we have 10 here. So we have 10 here in place of this. So we have 10 here. So from here we are getting 2 is equal to 2 plus c, or we can say that c is equal to 0. So the equation, our equation reduces to 10 upon y is equal to x, or we can write xy is equal to 10. Okay, so xy is equal to 10, that means option A is correct. Now we have problem number 9. If a to the power 1 to the power f a e to the power minus 1 upon x plus b is the solution of the differential equation, given differential equation, then suppose, let us now try to solve the equation. Dy upon dx is equal to y upon x square, or we can write it as dy upon y is equal to dx upon x square. So integrating both sides, we will be getting ln y is equal to minus 1 upon x plus some c. Okay, so which is equal to y is equal to e to the power c minus 1 upon x, which is nothing but a times e to the power minus 1 upon x. So we are getting y is equal to a e to the power minus 1 upon x, where a is real number, right? So, and of course there is nothing b, so b is 0. So from this we are getting b, option B as the correct one. Okay, now we have the last problem, problem number 10. The curve for which the normal at every point passes through a fixed point hk. So we have to find the equation of a curve such that normal at any point on that curve pass through this fixed point. Okay, so let us have a curve whose equation is y is equal to fx. So, and let us have a point say alpha beta on that curve. Then at alpha beta we have the equation of normal as y minus beta is equal to, where beta is equal to f of alpha. So let me write in place of beta, f of alpha is equal to, slope of normal is minus 1 upon f dash alpha, x minus alpha. Okay, so this normal always passes through a fixed point hk. So we have the equation, this equation will always satisfy this point hk. So we have y, in place of y we can substitute k minus f alpha is equal to minus 1 upon f dash alpha into h minus alpha. Now since this is general case for this curve, so here alpha is basically x coordinate and f alpha is y coordinate. So we have f dash alpha as dy upon dx. Now substituting this value on the above expression, we have k minus y is equal to minus dx upon dy into h minus x, or we can write k minus y dy is equal to minus h minus x dx, or further we can write it as x minus h dx plus y minus k dy is equal to 0. So integrating, we have x minus h square upon 2 plus y minus k square upon 2 plus some constant k is equal to 0, or we can write it as x minus h square plus y minus k square is equal to some constant, say c. So this is basically the equation of a circle. So also you can see that for a circle at any point, if you draw a normal, it always passes through a fixed point which is called center of a circle, right? So this is something like this, something like the case of a circle. So option C is correct here. Okay.